Okay, next talk is by Thomas about Damin.
Thank you. Right. Good afternoon. First, I need to apologize. I'll be swearing for the next 15 minutes. Unfortunate consequence of not protecting your main branch, lessons learned. My name is Thomas Michelat. I'm working for the data analysis group at the European Expo. And today I will introduce the data and metadata inspection interactive thing, which is definitely not a backronym for Damnit. But first, I will quickly introduce the context. If you're not familiar with the European Expo, there is very elaborate representation of the facility. We have currently 3 operational beam lines with 2 to 3 instruments as end station. And the machine produces bursts of photon bunch at up to 4.5 megahertz rates over a short period of time, and this is repeated at 10 hertz rates. And all those bunch are split across all of the beam time, and typically each instrument would receive a few hundred of FEL pulse at a 10 hertz rate. In terms of data workflow, we typically operate with a large detector that can operate in megahertz rate. With that bunch structure, the data is being streamed through data aggregator alongside with control data, and it can be further streamed to online computing cluster, which is used for correction of the data and visualization, and further data analysis for steering the operation during the experiment and have live feedback and be able to monitor what is happening. It's usually working on a small subset of the data because it's very hard to deal with the entire data that's being acquired in real time. The DAQ would also write subsets of the data for a certain period of time we call runs. So that's typically a few seconds to hours, in general a few minutes of data recording at a time, and that would generate a large number of HDF5 files. Those files would then migrate to a large computing cluster. We would run some correction for this big detector and generate another set of files, and this is like the basic set of data you would use for your processing then and publishing analysis, your result from your experiment. So what is Damnit there? There's typical pattern that user just open a Google spreadsheet and start filling run 1. Those are my parameters, my sample. Here it's the beam parameters, this happened, some comments and so on. And you have like one poor PhD student who spent the entire shift filling that table, trying not to make any mistake. So the original motivation is to free that poor student from this task and create those runs automatically. So that's what we did. We made a poor knockoff of Excel, but we integrated things that make it very useful during experiment. So it gets filled automatically. It's integrated with our system. I will go more into details with that. And it goes a bit beyond of what was in the original table. We can also run analysis and integrate those results within the same view alongside the metadata that's being collected. So that makes it useful during the experiment. It helps steer and interpret the data as you are acquiring it, and also can be used long after the experiment if you want to refine parameter, do some post-processing, adding some analysis afterward. This can also be integrated into this table to continue having the same interface to have an overview of the data. I will go backward. I will start to show some use case that has been done this year, and then go into details of how this works in the backend. So here we have an example of a XPCS experiment that ran this year. And you can see the kind of data that's being collected. So typically you can show the kind of scan that's being executed, the beam energy that was for the run, some motor position, the sample information you have, and so on. Also, you can integrate complex plots that result from very complex analysis that require distributed computing over many nodes on a very large amount of data. And having all of that metadata and analysis result all together really help having a good overview of what's happening in your experiment and makes it more enjoyable in terms of workflow. Another example here is for XS experiments. You can see a preview of a detector data, which is the average of every frame in a run, computing azimuthal integration over all of the frame in that run, in that case about 8,000, and then final result, which is the average difference between pump and probe signal for this run. Other things you can do is see trend of data over your experiment. So in that case here, you would see the beam energy, average beam energy per run over the full experiment. And you can do that with any kind of quantity you have put in your table. So I didn't ask for a workshop session, but here's a very express crash course on how you could write such code to generate those tables. So it's basically a Python file that you need to write. We try to make it as simple as possible, so any user who come for the first time would be able to add any quantity they want to monitor. So what's important here, you add this variable decorator to any Python function, and that's basically what makes a column in your table. You can have there are some attributes that let you customize how it looks like, so you can have nice title and other attributes. What's important here, the first argument of the function is a data collection from our extra data package, which is basically the way you would access to the data files at European Exfil. So we reused all of the library that exists already as a facility provided softwares. So there is technically nothing new to learn how to access the data. It's just putting any analysis you may already have in a Jupyter notebook or Python script. You could put simply that in function here and have the result directly fed into your table. And then your function does some analysis. In that case, I want to return one image of my detector, and this is, you can see a preview in the table for that run. And if you click on it, you can see the full size data and explore that. You can depend on results from other variables and generate complex workflows. In that case, here I have an argument with type annotation that says this is the data that's the result returned by the variable detector, and you can reuse that for further processing. And in that case, I produce a 1D integration of that image, and I return the 1D trace as a data result. You can see there is an extra argument here that's called summary, because I want to show in my summary table, I want to show the maximum value of that 1D trace. That's what's interesting. So that's what will appear in the table, and if I want to see the full data that is written by the function, this is still saved in files, so you can access it by clicking on the front end in that cell, and it will show the full trace of that data. So in terms of design, we use Kafka as a central broker. to exchange messages. So we have integrated that with the exfil system that exists. For example, DAQ, data migration system calibration. So when your data is available, those will send message. And on our computing cluster, we listen to these events, and if a context file exists for the proposal that has new data available, it will submit jobs on the computing cluster using Slurm, and this job would run the context file. The results are saved in HDF5 format, and upon completion, it would also send message saying that it's complete and what result exists. We currently have a Qt client that would listen to this message and feedback live updates to the user as the data is being processed. And we provide also Python API, which is very useful if you want to do further processing, reusing those results that has been processed by the Damnit software. We have further integration with more service. So for example, we can publish a run table in our electronic logbook and access a lot more metadata that's available in our metadata catalog. For example, related to sample information or experimental techniques. And we aim to export also a set of metadata that's specific to certain type of experiment in this metadata catalog to be compliant with open and fair data and make searchability, increase searchability of the experimental metadata. The next big development on the software is to build a web front end using React and Fast API. The architecture is quite standard. We have HTTP API that would read the data and get events, and a web UI server that would serve the front-end software. And you have a small sneak of the current state of the front-end development. And the main reason we want to do that is because it increases accessibility. Anywhere people can just take their phone and get the table. At the moment, having a remote desktop session, opening a Qt application is less than ideal. So that's why it's our main next target. But you have a lot of more things we want to do, among them grouping of runs. So we might want to have different level of granularity, or we want to compare a set of data with certain characteristics. We want more integration with sample database and, as I mentioned, our metadata collections. And we want to also increase the reproducibility capability, for example, by storing different version of the variable you would produce with a different set of parameters you have, of different algorithms you want to apply to them, and be able to compare results between those. To summarize very quickly then, Damnit currently offers a processing framework that is very flexible and execute user-defined code. And it's built on top of our analysis ecosystem that's been developed for years already. It currently has a Qt application front end to show the run table, the experiment overview, and let you explore the variables data. Hopefully this will be replaced soon by a web application, as well as Python API to access process data. Important, this is used at every instrument at European X Fair. Sometimes just to collect some simple metadata, but for certain type of analysis, most of it is done through Damnit. If you're curious, you can check out our GitHub page. It's an open source project, and you can contact us through this email address. Thank you.
A very good timing. So, open question.
Nice presentation. So the question is very simple. What is the feedback of the PhD student that was written this table before?
Well, hopefully he has time to do better things, or he can rest. But, yeah.
In general, the feedback is, I mean...
The feedback is usually very good. So our first main user for this are our beamline scientists, and they're very excited to use that. I mean, at least the one I interact with, they adopted it basically for, not necessarily for user data, but for their machine control monitoring, and a lot of users also who already used it. So there are some kind of experiment where we developed already very complex analysis, typically the XPCS experiment. We have an analysis software designed there. And yeah, once it's integrated, user also really liked it.
On slide number 15, you showed that you express workflows as code. Yes, exactly here. I was wondering where the parameters of this workflow go. For example, if you're integrating a diffraction, an image, I'm pretty sure you're going to need the geometry of the detector. So anyway, so a workflow in general has parameters. How do you provide those?
Parameters currently are defined. So you can enter parameters that are kind of columns on the table. So those would, you could have a parameters that define a path to a geometry information. This needs to be improved as well. Like we have plans to make it more parameterizable. But this is the way. It could be also simply attributes in this Python file that defined the context file would define the geometry you need to use for. So it's not perfect at the moment because you will need to define. It's a bit hacky at the moment to define which geometry you need for which run. You need to map that somehow. At the moment, it's not well integrated into it, but that's also on our to-do list there to improve on that.
Okay, so I could imagine this would be also useful for checking the quality of the data, or also implementing the new EU XFL data policy to delete data which is not good.
There is another approach for that, but yes, that's all. We could also. I think it's probably a good idea to use that for data reduction, like not data that is not good, but since the data we generate with that software is a data format we support as a facility, the user could decide the result that is stored in Damnit is what I want to keep as final result, and you could come from a proposal that 1 petabyte of data to a few 100 gigabytes, and that would be a very, very strong data reduction ratio already.
Okay, thanks, Thomas. Okay. Sorry, probably we have stopped that.
Right.
Okay, thanks.
Thank you.